volt-ampere rating of a circuit indicates the amount of power it can manage. The amp rating of a circuit signifies the amount of current it can handle. The relationship between volt-amps and amps is described by the equation volt-amps equals amps times volts. Considering a 120/208 volt Y service, an 8 amp circuit operates at 120 volts. The volt-ampere rating for that circuit is calculated as 8 amps multiplied by 120 volts, resulting in 960 volt-amps. The amp rating of the circuit is calculated by dividing the volt-ampere value by the voltage, which is 960 volt-amps divided by 120 volts, equaling 8 amps. When determining the total amps for a panel, adding up the amp ratings of all the individual circuits is performed. However, the volt-ampere rating of the panel is derived from the summation of the volt-ampere ratings of all the circuits within the panel. It's important to recognize that the amp rating and the volt-ampere rating of the panel are not equivalent. The variance arises from the fact that the volt-ampere rating reflects the panel's overall capacity to handle power, whereas the amp rating is a measure of the panel's capability to handle current flow. These two ratings are not directly interchangeable. For a 120/208 volt Y service example, if a single circuit has a volt-ampere rating of 960 volt-amps, and if that was the only load on the panel's volt-ampere rating is 960 volt-amps. However, calculating the panel's amp rating involves taking the volt-ampere value and dividing by a factor that considers the three-phase nature of the 208 volt service, specifically the line-to-line voltage of 208 volts, and the square root of 3, which is approximately 1.732. This is approximately 360 volts. Therefore, the panel's amp rating is determined by dividing 960 volt-amps by 208 volts multiplied by the square root of 3, which is approximately 360 volts, resulting in approximately 2.67 amps. The reason that the panel's amp rating is approximately one-third of the sum of the individual circuit amp ratings in the panel in this simplified example is fundamentally because the panel's volt-ampere rating is, in a similar proportion, one-third of what one might intuitively expect if directly summing the volt-ampere ratings without accounting for the three-phase voltage characteristics. To elaborate on this concept, it is important to understand the relationship between single-phase and three-phase power calculations. Firstly, in a single-phase circuit, the power in volt-amps is simply the product of the voltage and the current. However, in a three-phase system, such as a 120/208 volt Y service, the power calculation is more complex because the voltage between any two lines is higher than the voltage from any line to neutral. Secondly, in a Y configuration, the voltage from any one of the three lines to the neutral point is 120 volts, but the voltage between any two of the three lines is 208 volts. This is where the square root of 3 comes into play because it is the mathematical factor that relates the line-to-neutral voltage to the line-to-line voltage in a balanced three-phase Y system. For three-phase power calculations, the total volt-amps is equal to the square root of 3 multiplied by the line-to-line voltage and then multiplied by the line current. The line current here refers to the current flowing through each of the 3 lines feeding the panel. The formula highlights that for the same amount of volt-amps, the line current in a three-phase system will be lower than the current in a comparable single-phase system because the voltage is effectively higher due to the three-phase configuration. Thirdly, consider a simple scenario where you have 3 identical 120-volt loads, each drawing 8 amps, connected to a 120/208 volt Y panel. Each load is connected between one of the 3 lines and the neutral. The volt-ampere rating of each load is 960 volt-amps as calculated earlier. If you were to simply add up the volt-amps of the 3 loads, you would get 2880 volt-amps. However, the panel's total volt-ampere rating is not simply the sum of the individual volt-amps. Instead, it is calculated using the three-phase power formula. To find the line current, you would rearrange the three-phase power formula to solve for current. That would be the total volt-amps divided by the square root of 3 and then divided by the line-to-line voltage. If we assume the total load is balanced across the three phases, which means each phase is carrying an equal load, then the total volt-amps seen by the panel would indeed be 2880 volt-amps in this particular scenario. In this case, the line current would be 2880 volt-amps divided by the square root of 3, and then divided by 208 volts, which gives you approximately 8 amps per line. This may seem counterintuitive, but it is because the loads are connected line to neutral. In a more complex scenario, with a mix of 120 volt and 208 volt loads, the calculation becomes more involved. However, the underlying principle remains the same. The panel's total volt-ampere rating is the sum of all the individual load volt-ampere ratings, taking into account whether they are connected line to neutral or line to line. The panel's amp rating, which is used for sizing the main breaker and the feeder conductors, is derived from the total volt-amps using the three-phase power formula. It is important to note that electrical codes such as the NEC or National Electrical Code provide guidelines and requirements for calculating panel loads and sizing conductors and overcurrent protection devices. These codes take into account factors such as demand factors, which allow for reductions in the calculated load based on the assumption that not all loads will be operating at their maximum at the same time. Furthermore, it is always recommended to consult with a qualified electrician or electrical engineer for any electrical work to ensure compliance with all applicable codes and safety standards. The concept of power factor also plays a crucial role in understanding the relationship between volt-amps and watts. Power factor is a measure of how effectively electrical power is being used. In a purely resistive circuit, such as an incandescent light bulb or a heater, the voltage and current are in phase, and the power factor is 1.0, or unity. In this case, the volt-amps are equal to the watts. However, in circuits with reactive components, such as inductors or capacitors, the voltage and current are out of phase and the power factor is less than 1.0. This means that some of the current is not doing any useful work, and the volt-amps are greater than the watts. For example, an electric motor typically has a power factor of around 0.8, which means that for every 100 volt-amps of power being supplied to the motor, only 80 watts are being used to do actual work. The remaining 20 volt-amps are being used to create and maintain the magnetic field in the motor. Power factor correction can be used to improve the power factor of a circuit, which reduces the amount of current required to deliver the same amount of power. This can result in lower energy bills and improved system efficiency. In commercial and industrial settings, power factor correction is often achieved by installing capacitors in the electrical system. These capacitors provide reactive power that cancels out some of the inductive reactive power, bringing the power factor closer to unity. To summarize, the relationship between volt-amps, amps, and voltage in a 120/208 volt Y service is governed by the principles of three-phase power. The total volt-ampere rating of a panel is the sum of the individual load volt-ampere ratings, while the panel's amp rating is derived from the total volt-amps using the three-phase power formula. It is important to consider the power factor of the loads when calculating the total volt-amps and amps, and always adhere to electrical codes and consult with qualified professionals to ensure safe and compliant electrical installations. Considering demand factors in electrical load calculations is crucial for efficient and cost-effective electrical system design. Demand factors are essentially multipliers applied to the total connected load of a building or facility to account for the fact that not all electrical loads operate at their maximum rating simultaneously. This is based on statistical analysis and empirical data that shows that the actual peak demand is typically lower than the sum of all connected loads. Electrical codes, such as the NEC, provide tables and guidelines for applying demand factors to various types of loads, such as lighting, receptacles, heating, ventilation, and air conditioning, or HVAC, equipment, and motors. The specific demand factors vary depending on the type of load, the size of the load, and the occupancy of the building. For example, lighting loads in an office building may have a demand factor of 0.8, meaning that the calculated load for lighting can be reduced by 20% when determining the total service load. Similarly, receptacle loads may have a demand factor that decreases as the number of receptacles increases. HVAC equipment and motors also have demand factors that depend on their size and duty cycle. Applying demand factors correctly can significantly reduce the calculated service load, which in turn can lead to smaller conductor sizes, smaller overcurrent protection devices, and lower equipment costs. However, it is important to exercise caution when applying demand factors and to ensure that the calculated load is still sufficient to meet the actual demand of the building. Overly aggressive application of demand factors can result in an undersized electrical system that is unable to handle the actual load, leading to voltage drops, overheating, and even equipment failure. In addition to demand factors, diversity factors are also sometimes used in electrical load calculations. Diversity factors are similar to demand factors, but they apply to the loads within a specific piece of equipment, such as a panel board or a motor control center. Diversity factors account for the fact that not all loads within the equipment operate at their maximum rating simultaneously. For example, a panel board serving multiple branch circuits may have a diversity factor of 0.7, meaning that the calculated load for the panel board can be reduced by 30%. Like demand factors, diversity factors should be applied with caution and in accordance with applicable electrical codes and standards. To accurately determine the appropriate demand factors and diversity factors for a specific electrical system, it is essential to conduct a thorough load analysis. This involves identifying all of the connected loads, determining their individual ratings, and estimating their operating cycles. It may also be necessary to collect data on actual load profiles using data loggers or energy monitoring systems. The load analysis should also consider future growth and expansion. It is important to design the electrical system with sufficient capacity to accommodate future loads, even if they are not currently known. This can be achieved by oversizing conductors, overcurrent protection devices, and equipment, or by designing the system to be easily expandable in the future. In summary, demand factors and diversity factors are valuable tools for reducing the calculated service load and optimizing the design of electrical systems. However, they should be applied carefully and in accordance with applicable electrical codes and standards. A thorough load analysis is essential for accurately determining the appropriate demand factors and diversity factors and for ensuring that the electrical system has sufficient capacity to meet the actual demand of the building, now and in the future. Understanding the impact of harmonics on electrical systems is another important aspect of electrical engineering. Harmonics are sinusoidal waveforms that are integer multiples of the fundamental frequency of the power system, which is typically 60 Hz in the United States and 50 Hz in Europe. These harmonic frequencies can distort the sinusoidal waveform of the voltage and current, leading to a number of problems. Harmonics are primarily generated by nonlinear loads, which are loads that draw current in a non-sinusoidal manner. Common sources of harmonics include electronic devices such as computers, televisions, and LED lighting, as well as variable frequency drives, or VFDs, used to control the speed of motors, and uninterruptible power supplies, or UPSs, used to provide backup power. The presence of harmonics in an electrical system can cause a variety of problems. Firstly, harmonics can increase the current flowing through conductors, transformers, and other electrical equipment. This increased current can lead to overheating, insulation breakdown, and premature equipment failure. Secondly, harmonics can cause voltage distortion, which can affect the performance of sensitive electronic equipment. Voltage distortion can also interfere with communication systems and other electronic devices. Thirdly, harmonics can cause nuisance tripping of circuit breakers and other overcurrent protection devices. This can disrupt operations and lead to downtime. Fourthly, harmonics can cause increased energy losses in the electrical system. This is because harmonic currents flow through the impedance of the system, causing additional heat losses. To mitigate the effects of harmonics, a number of techniques can be used. Firstly, harmonic filters can be installed to reduce the amount of harmonic current flowing in the system. Harmonic filters are typically composed of capacitors and inductors that are tuned to specific harmonic frequencies. Secondly, harmonic mitigating transformers can be used to reduce the amount of harmonic voltage distortion. Harmonic mitigating transformers are designed to have a high impedance to harmonic currents, which reduces the amount of voltage distortion. Thirdly, nonlinear loads can be replaced with linear loads, which draw current in a sinusoidal manner. This can be achieved by using power factor correction capacitors or by replacing electronic devices with more efficient models. Fourthly, proper grounding and bonding techniques can be used to reduce the amount of harmonic current flowing through the grounding system. This can help to prevent nuisance tripping of ground fault circuit interrupters, or GFCIs. To assess the level of harmonics in an electrical system, harmonic analysis can be performed. Harmonic analysis involves measuring the voltage and current waveforms at various points in the system and then calculating the harmonic content. This can be done using a harmonic analyzer, which is a specialized instrument designed for this purpose. The results of the harmonic analysis can be used to identify the sources of harmonics and to determine the appropriate mitigation techniques. In summary, harmonics are a common problem in electrical systems that can cause a variety of problems. Harmonics are primarily generated by nonlinear loads and can be mitigated by using harmonic filters, harmonic mitigating transformers, linear loads, and proper grounding and bonding techniques. Harmonic analysis can be used to assess the level of harmonics in an electrical system and to determine the appropriate mitigation techniques.